Alrighty, good morning, everybody, and a happy Thursday. Thank you all for joining us today on the seventh tech webinar this year. My name is Anthony Connors, and I'm the regional field engineer for the Michigan and Toledo area, and I'm going to be your host for today. And real quickly, I'll just go over a couple things here that you might be noticing if you're new to these types of events. You probably already noticed this, but your camera and microphone have been turned off. And hopefully on the right side of your screen, you should be seeing a handy Q&A feature. If you have any questions that come up during the presentation here, you can feel free to submit them there with your first and last name as the presentation is going on, and we're going to take some time at the end of the presentation here to answer your questions. And if for some reason you don't see that function, you can always email your questions to solutions.michigan@swagelok.com, and then we're going to add your question to the list for our presenter here. But with that out of the way, I'll now welcome back Chris Kiesling here. Chris has spent many years managing multiple plants and facilities, getting them all prepped up for the winter before eventually joining the Swagelok team here as our operations director just over 3 years ago. So he has plenty of experience in today's topic, which will be steam tracing. But without further ado, Chris, you can go ahead and start.
Yeah, hey, thanks a lot, Anthony. And yeah, I think that's true. This is a topic that's pretty near and dear to my heart after many years of dealing with steam systems and heating systems and plant winter operations. So our goal here today, here's sort of the what, when, and why of today's presentation. So what we're talking about today is installing and maintaining steam trace systems. When do we want to do that? We want to deal with our steam tracers anytime we work on a system, but we're also going to have a focused effort around steam tracing and around heating systems in the fall time to prepare for winter. Why do we do all this? Well, our goal is ultimately to keep the fluids in our system above solidification temperatures and ensure smooth operation. So not just solidification, but also thickening or any other sort of things that could happen that could impede, say, pumping operations or any other sort of operational consistencies. We're going to talk today about components of a steam tracing system. We're also going to go over guidelines for effective use of steam tracers. All right, so why is this so important? Well, inefficient cold weather operation can be very, very costly. So this is an example of a survey that we did. And if you joined us for our winterization webinar last year, you probably saw this as well. So this was a survey that was done by our energy audit team and checked mostly steam traps in this case. But just on steam traps alone, we found about a 17% failure rate. It's pretty common in a lot of facilities. If you just take a snapshot, you could have anywhere between 5 and 20% of your steam traps in some form of failure. Based on the failure rate and the failures that we found, there was an estimated loss of about 2,000 pounds per hour of steam, which equated to $130,000 a year in total losses. So it can be a big financial hit. But in addition, folks, especially on the tracers today, freeze-ups can affect production and or quality. So that could have you shut down part of the plant or do bypassing or run at a slower rate because a line is froze up or you can't pump as fast through it because you've had thickening effects. And that's what your tracer are going to help to prevent. You also have to remember that every leak poses a safety concern. So whether it's building a large icicle or an ice monument up high that could possibly fall on somebody or causing slippery surfaces, we want to stay ahead of those things at all costs. You know, there's a lot of times I've seen in facilities where you have a large leak that's up in a higher area and it ultimately leads you to have to rope off a large section or keep people out of there to be safe. And they become a real pain in the butt to take them down and to deal with them. So moving on from the system itself, so why saturated steam? So generally for tracing systems, saturated steam is highly advised. And so we want to talk a little bit about why we use saturated steam specifically. So what we're trying to do with a steam tracer is to transfer heat. So ultimately, we're not looking to heat things up. We're not looking to necessarily add heat to what's on our pipeline. We're looking to just maintain the temperature that's in there as the product flows. So our goal is to transfer as much heat as possible. And saturated steam is going to be very efficient for that because we take advantage of the latent heat of vaporization. That's pretty much the most efficient way you can deal with this. So we've got a chart here and it shows kind of, this is for any general material, but we're going to deal with water, which would be ice as a solid. So if you start as a solid, as ice, you add heat to it, eventually you're going to get to this melting phase. Well, during the melting phase or freezing phase, when you have both phases available there, you're not going to change in temperature very much. You're just going to add a lot of, oh, sorry about that. I'm having some sort of thing going on with my slides here. Okay, sorry about that. Now we're back at it. So again, we're going to have here is that we're going to have some sort of melting or freezing. We're not seeing much temperature change of the fluid itself, of the solid, but that's where there's a lot of heat being added or being taken away to cause that melting or freezing action. But really what we're going to focus on is on the other end. So we have steam, which is gaseous water. And if you look at temperature change only, the superheated steam, anything that's above the vaporization temperature, as you absorb temperature from it, you're going to move down this curve. But if you think about, if I move down, say 20 or 30 degrees down this line, it's not actually taking a lot of heat out, or it's not adding a lot of heat to my process. So heat is what we really care about, is energy transfer. So that temperature change represents a small amount of energy transfer. A much larger energy transfer is if we start with saturated steam, which is starting at this point right here, at the saturation temperature and pressure. And we want to basically make a phase change happen. So we want to condense the steam into water, into liquid. And as we condense, we're absorbing a lot more heat into our process lines. So that's going to cause a lot more of an effect when it comes to actually keeping things warm and keeping things heated. Now, the downside is we are forming condensate. So we're going to have to deal with those. And we're going to talk a little bit more about that in just a second. So what are our main components of a tracing system? Our main components, generally we're going to have some kind of isolation. This is an example of a tracer layout. So you have isolation valves on both ends. So you've got them on the front side, and in this case also on the back side, to be able to isolate the tracer for maintenance, and also the connecting components. You have the tracer itself, which is generally going to be some type of a tubing to be able to flow steam or flow fluid through it. You're going to have your connection system, whether that be a ferrule system, a compression system, or some other type of means, but you're going to have some means of connecting all those tubing pieces together, because you're probably going to have to use multiple tubing pieces to trace a line. And then finally, you're going to have a steam trap. The reason for the steam trap is to keep steam flowing when necessary and to shed any of that condensate to where we want the condensate to go during the process. Now, what the tracers or what the trap's going to do, it's going to guarantee that we're taking advantage of that latent heat of vaporization for the steam heating application. So they're pretty key and pretty important in getting a very effective steam trace. If we didn't have the trap, the steam would just blow through there and we wouldn't absorb very much heat from it at all. So this forces the system to absorb that latent heat of vaporization. So onto the tubing side. First off, just a quick question of why do we use tubing? Well, tubing is pretty easy to work with in this type of a format. We've got a couple of examples down here of steam trace systems, and it's really easy to bend tubing. If you thought of, like, saying using pipe or some other application to go over top of these larger diameter pipes, it's not going to be as easy to do a tight radius bend and kind of put the tracing where you need it to keep your components hot. It's also easy to connect, and another nice advantage is you can use coiled tubing. So you can order a large, 1,000-foot coil or something and have a continuous run where you're just laying it out and not have to connect a bunch of pieces together. For times when you're doing a much longer line, those are always available. From a material perspective, generally the most common is going to be copper or stainless steel. Stainless steel has got a lot of advantages to it. Copper is nice, and you can see copper in this photo. One nice thing is it's very easy to bend because it's so soft, but it doesn't have the longevity or the rigidity once it's installed as stainless tends to have. Stainless is going to be a lot better because you're not going to have to paint it, so there's no worry about it corroding from the outside. You're also going to have resistance to carbonic acid attack. Generally, steam condensate is going to form carbonic acid and be mildly acidic. So the one thing we want to avoid is we don't really want to use carbon steel piping. Even if you're to use carbon steel tubing on the system and paint over top of it, because of the thermal expansion, it's going to heat up and cool down between summer and winter a lot. You're going to see that paint degrade pretty quickly. So one of the things on this picture on the right here, you'll see unions that are being used at all the joints. It's a pretty good best practice. And then also to run those unions outside the insulation. So this doesn't have the insulation over it, but you can see the unions are up much higher than where the insulation is going to run. That's going to allow us to disconnect the unions if we ever have to take out this spool of pipe for maintenance, instead of having to cut our tracers and then reinstall them or add unions later, clean up the joints and all those things. So again, a little planning for the future there. We want to always insulate after the tracing. The tracer alone isn't going to impart enough heat to keep the process warm. You're going to still have condensation and potentially hardening. So you really want to make sure you insulate. The tracer is just going to help that insulation be more effective. Then finally, one trick here is also spacer addition. You can actually see it on this system down here. Now, This is kind of a controversial topic. People go both sides of this. Some people say it's not necessary, it's an old technology. Some people say you absolutely can't run a tracing line without it. Well, one spot you want to think about with a tracer is when you're using dissimilar metals. So say you're tracing a carbon steel pipe with stainless steel tubing. If you don't have some kind of a spacer there, just from the vibration in the facility and the natural expansion and contraction as things heat and cool over the year, you're going to have a little bit of rubbing between the materials. If you have that carbon steel painted and the paint rubs away and you have direct contact between the stainless steel and the carbon steel, you can have galvanic corrosion, which could lead to a leak. I've seen it happen in facilities before. So a lot of facilities I've been familiar with, that's just a cardinal rule, is you always use spacer blocks in order to prevent that. Now, the challenge is they're kind of a pain in the butt to install and keep in place after they've been installed. You can see somebody did a really, really good job here with the strapping at every single spacer block. So on the topic of tubing, we mentioned that tube fittings, it's easy to install and it's very modular. And so that's one of the advantages of using tube fittings specifically. Tube fittings are also less susceptible to pressure and temperature swings and resistant to vibration as well. And part of the reason for that is because of the ferrule design itself. And if we zoom in right here on the back ferrule, one nice thing with tube fittings is the back ferrule is really what's providing the grip. And because of the hardening differences between the back and front ferrules and the ferrules and the nut, it's going to be inherently vibration and resistant. So we see that as a big advantage over especially NPT as an example, which tends to like to unwind over the course of a lot of heating and cooling cycles and with natural vibration in the facility. The other nice thing with compression over top of say NPT is with compression, the threads are purely mechanical and providing the mechanical support for the system. The sealing is being done by the ferrules versus, for example, in NPT, where the sealing and the grip are both being provided by the threads. So if you have any movement at all of those threads, you're also losing your seal, not just your tightness. Now, another nice thing about using tube fittings is that it's a modular design, so you can do easy system modification. We've used this in a couple of webinars before, but you could easily go from, say, an elbow to a T. They have the same stack height just by simply removing the elbow, dropping a T, and then running your secondary line. So if you want to expand your system or add on later, that's available to you. So moving from the fitting components over to steam traps themselves. So two main styles that you see, especially for tracer lines, are going to be either thermodynamic or thermostatic. So I just want to take a minute and kind of talk about the differences between the two. I think they get confused pretty frequently. The thermodynamic trap is similar to what we show here. They're going to be pretty common, especially in industrial applications and a lot of heating applications. Thermodynamic traps, they use a nozzle technology inside to basically vaporize a little bit of condensate and create steam pressure inside the dome. That's going to relieve at approximately the steam temperature. So what's going to happen here is as you have condensate being allowed out, like in this first photo, it's going to float this disc upwards, and then eventually enough flow of the condensate, you'll get some steam flowing out. It's going to heat up the condensate in there. That develops steam pressure above the disc, which shuts the disc and closes it up. And you have basically a little bit of steam inside the control chamber. As the thing sits here for a while, it slowly condenses. And once you don't have any steam pressure in here anymore, it allows the pressure inside the system to push it back open and let more condensate out. The difference with thermostatic is thermostatic actually work off of differential temperature. So they can actually run at lower temperatures. So the thermostatic, in that case, it'll have sort of a plug that's on an expanding, and I didn't have a really great photo of this, but it was it'd be like a plug that's on kind of an expansion joint. And as the expansion joint heats up, the plug expands and it plugs off. Well, then the trap holds condensate inside of it, and it'll cool down over time until you hit the temperature it's set for, and then it will contract, and that will cause the plug to release and allow more steam through. So it's working off true differential temperature. So the nice thing on thermostatic is you can run those at lower temperatures, not just the saturation temperature of the steam. And so those are good for lower temperature applications for tracing. The thermodynamic are the ones we're going to look for higher temperature or higher flow or higher heat demand in our tracing systems. So what are some of the failures that can happen? Generally, we're going to see one of two things happen with most traps. Either they're going to blow through, so they're just letting steam through all the time, which is going to be very inefficient. Again, we're not getting that latent heat of vaporization. We're just getting hot steam blowing through and contacting, so you're going to waste a lot of energy. Or the other thing that's possible is they just don't open at all. They're completely locked up. So what to check and what to look for on those, On all your traps, you should expect them to relieve a little bit of steam condensate with a little puff of steam and then stop. And they should relieve and stop and just cycle like that over and over again. The frequency might be longer. It might relieve for even a full minute and then stop for a full minute. So you'll have to watch it for a while to see that frequency. So you want to be able to watch the trap just naturally operate. It's very hard to do if your condensate system is fully enclosed. So that's one of the things you're going to look for. You're also going to look for temperature. If the thing's ice cold or if it's ambient temperature, even this time of year when it's 70 degrees, then that means there's probably nothing flowing through it. If there's nothing flowing through it, something to check, especially on thermodynamic traps, is these filters here. So very, very frequently, this filter is all clogged up or completely plugged. It's a pretty simple task to just isolate that, take it out, and service it. Again, your steam systems will have a little bit of degradation inside the piping here and there, and you'll be surprised at how much crud can build up, which is the reason why we have these screens in here. A little thing on trapping best practices. So you want to think about testing and replacement when you're installing your system. So this is an example of a system, a steam trap system coming off a steam main. So this is great because they put 2 block valves here, so you can isolate your steam trap. The steam trap's right here in the middle. And they also have here this component, which is hard to see what it is, but that's actually a sight glass. So what that allows you to do is look inside here through a window and see, is there condensate flowing through here periodically? Now, sight glasses aren't always great. They tend to plug up, or they tend to haze up over time and be hard to see through, depending on the application. So one thing that we offer here, another option instead of the sight glass, is put a TN with a valve. And what that allows you to do is you can turn off the condensate downstream line and open up this vent valve. And when you open that vent valve off the trap, you should be able to see the steam trap cycling. So it gives you a visual indication that the steam trap is cycling properly and not blowing through. One product that we have here are these steam trap test stations. They're pretty popular because that whole process is integral into this nice compact body. So you actually attach your steam trap to the other side of this flange here. It's a standard flange. It has the filter integrated in the bottom right there. What this also does is this is a ported ball valve, so you can close this downstream line and it actually opens up the trap itself to this tube going out of the bottom. So what that does, if you leave the inlet side open, it allows you to do a visual test on your steam trap right there on site. It's also got the 2 isolation valves, so you can close them both and lock them out in this case, and it vents the trap anytime that the valves are both closed, so it'll prevent you from freezing if it's blocked in. And it'll also allow you to verify that the steam trap has been vented and that there's no pressure in the system. So pretty handy tool right there that integrates a bunch of components right into it. So finally, one thing to think about on your steam systems is using manifolds. I see this in a lot of facilities, but maybe not laid out extremely cleanly. So it's going to help you with the layout of your tracing system, make it much easier to trace and to understand what goes where and how to isolate a tracer when you need to work on a single pipeline. Condensate manifold on the return side of the tracing system, you can also use that, and this shows an example where we've integrated a steam trap test station into it. So this allows you to kind of do both things. And now if you have 2 manifolds like this, another tip that I put out there is to keep your system organized. If this is the feeder side, the top right valve, make that one terminate to the top right valve on the other side. So keep them the same on both sides. So make it a lot easier to trace down when you have to isolate the system. Can't believe how many times in my life that I've been out trying to isolate a steam trace system and have tracers ran from 5 different valves in 5 different locations going onto the same pipe. Can be a real headache and eat up a lot of time. So keep them organized the best you can. Finally, one other tool that you guys can use is our resources and our folks here at the office at Swagelok, Michigan, Toledo. We have a comprehensive set of assessment tools, including ultrasonic detection and writing up cataloged reports, and sometimes just simple steam surveys that we can do for you guys that can help prepare and help identify any sort of issues in the system. We love to spend time on site and support these activities for our customers, and we can find a lot of savings at most of the facilities we go into. So also remember, these are not just for steam systems. You know, compressed air and industrial gases, there's a lot of money involved in those as well. So we can do similar energy and leak detection audits for you guys on those types of systems if you're interested. If you're interested in those types of services, you can reach out to us after the webinar or talk to your salesperson. So to review, our goal here was to talk about installing and maintaining steam tracing systems. We want to do that throughout the year. So when we maintain a pipeline, we want to make sure if we take the steam tracers off, we reinstall them or make sure they're ready to go. We're going to do that big push in the fall. Our goal is that we want to ensure consistent operation and ultimately save some money. So remember, we're here to help. Please reach out for any sort of deeper discussions or to schedule a meeting.
All right. Yeah. Thanks, Chris. Looks like we lost the presentation again. But yeah, we're gonna take some time here to answer some questions. Looks like we got a couple in the feed here while Chris is pulling this back up. Thank you all, and I do want to remind you guys that if you do have a question, you can submit it here, and we'll add it to the list. Just going right into it, Chris. Here we got Cole. Cole's asking, which heat tracing system is most effective, steam or electric?
Yeah, that's a great question. So that's going to vary pretty heavily from facility to facility. So certainly one part of the thing you have to consider is availability. So if you don't have a lot of electric power available, that can be a challenge. And if you have steam available, that might be a more effective way. But if you don't have steam, you're pretty much stuck with the electric side of things. I guess one word of caution I would say is, I think that you also have to think about what sort of maintenance forces do you have, because you're going to have to touch your tracing systems either way. So if you struggle to get all of your pipe fitting work done, probably an electric system, if you have a really strong electrical group, might be a little bit better of an option for you. One thing to remember is that electric systems do have a pretty huge draw. So we were struggling with steam systems in a plant I worked in, and we were trying to switch everything over to electric heat trace. But we found that we were starting to tax our substations pretty heavily because we were adding so much electric load just through those heaters. They draw a lot of current, so just be ready for that. And also can be very costly compared to what your cost of steam generation is at your boiler house.
Got it, yeah, thanks. Moving on here, we got next question from Jamie. And Jamie's saying, between copper and stainless steel tubing, is there an advantage of using one over the other?
Yeah, I think I hit on that a little bit. So copper, really easy to bend, really easy to install, but it's going to be susceptible in a lot of environments, especially industrial environments, to tarnishing and to corrosion. And also, it's not going to have quite the pressure containment that you're going to have with stainless steel. So the other thing to remember is you're working with a mixed media, you're working with steam and condensate when you're working with a tracer. So the simple pressure ratings, you want to go to much higher ratings when you're dealing with that because you can't get flashing and water hammers. So like I said, copper is very, very easy to install. And if you, say it's an indoor application or you don't necessarily have a lot of environmental effects, that can be very effective for you. But most facilities, most larger industrial facilities I've dealt with, we've typically used stainless steel.
Gotcha. Yeah. Pros and cons to both. Moving on here, we got Peter. Peter's asking, does Swagelok sell steam trace tubing? What lengths can I get?
Yeah, so we do. We have certain tubing sizes. So I believe we have from all the way down an 1/8 of an inch all the way up to 3/4 of an inch. And we call that our traced bundled tubing. So it also has a tracer line right inside of it. And you can select that internal tracer line to be copper or stainless, depending on your application. And we also, for the folks who asked about the electric tracing, we also have it with an electrical application. As far as the total length on those, I would have to look at the catalog on that one. But I believe most of them are right around 1,000 feet. You can get as a big spool. It comes pre-insulated on basically a big coil. I think they run, it's like I said, it's typically between 800 or 900 feet up to, there are a couple, and I believe it's the 1/4 inch tubing that get all the way up to like over 2,000 feet. You can get in one continuous length. But a lot of options there. You can also get shorter lengths than that, obviously. If you order it in 100 footers, that's kind of more of a standard length. It's maybe a little easier to deal with or a little easier to get in. Because they do get pretty heavy pretty fast.
Yep. All right. Moving on, we got Jerry, and Jerry asks, we use needle valves on a few of our steam lines, and it seems like they are always leaking. Are we using the wrong valve?
Okay. I guess this is one of those ones that I can always say the classic answer of maybe. It's possible that it's the wrong valve application. It's also possible, I think the challenge too is that when you say it's leaking, not sure if it's leaking by, like, is it leaking by the seat and not performing correctly, not isolating, or is it actually the end connections are leaking? Mm-hmm. So certainly if the end connections are leaking, it could be an installation issue. And so that's one thing you want to check for. Also, if you're looking at, say the packing is leaking on the valve, on the stem packing, that could be either the wrong valve, like the wrong packing material, or it could also be just the packing needs maintenance and needs tightening. If the valve itself is leaking by, like it's not isolating correctly or controlling correctly, then it is very possible that it's the wrong valve, the wrong application. You might need something a little heavier duty. The steam can, I mentioned, be corrosive because it does tend to run a little bit lower pH. Also, you can get a lot of different contaminants in your steam system. So even with stainless steel, one thing you might want to check is look for chloride cracking. Ideally, in your boiler feed water, you should be treating for chlorides, but it's possible. I've seen steam systems where you test the condensate and it's high chloride for whatever reason. So again, you can have all kinds of other trace things that can interfere. So material compatibility can be an important thing, and that probably does get back to that, am I using the right valve? But generally, you do want to use a heavy-duty valve. I think for us, it's the boy, Anthony, it's escaping my mind now. The needle valves, the severe service needle valves.
Yep.
So that's what we usually, I believe they're the N series that we're usually recommending for those types of applications.
Yeah, and does it make sense to use a needle valve as opposed to a ball valve? Doesn't matter which one you actually pick.
Yeah, so I think the big thing you got to look for is flow rate and CV. So you get back to the CV sizing, and for more information on that, we've done a couple webinars on sizing, or reach out if you guys have questions. I think the ball valve's much better option for just straight shut off, on and off. One challenge with these steam systems is some of them are very high temperature. So when you get to the higher pressure and higher temperature systems, the nice thing with the needle valves is you'll see metal to metal seats. So you don't have as much elastomer in there. So they'll have higher temperature ratings in some cases. So I think a lot of folks are stuck with needle valves or globe valves. I see very commonly too. I don't know. I guess gate valves, I've seen those before in steam systems, just not as common, even in the larger stuff. But yeah, the ball valve, one of the challenges there is you're not always going to get such a high temperature rating. So sometimes you're forced to go with the needle valve. Challenge with the needle valve is you're going to have more flow restriction because it's not wide open like a ball valve is inside.
Gotcha. Yeah. Okay. Thank you for the clarification there. All right. Looks like we got one more here from Anonymous. Oh, nope. It says Ray. Ray's asking, can a hose be used for tracing?
Yeah, so technically you could. The challenge with a hose is it's not necessarily made to transfer heat. So the hose is going to have a lot of layers in it, and a lot of times those are going to hold heat in. So what you really want with your tracing is you want as much heat as possible to get to the pipe or to the material, or the item that you're tracing, putting the tracers on. So in that regard, I think that you want to you probably would want to avoid hoses. Now, we've had customers who have used all metal hoses and been very successful at it. So it's worked out for some folks. And I will say, when I ran plants, one of the things we did to prepare for winter was we would order a couple of pallets of steam hoses, because if something froze up like a valve or something, because something failed overnight, you can just wrap a steam hose around it and put some insulating blanket over top and just get it hot again and get it back running. So definitely works for emergency. I've done that firsthand. But again, the hose on the outside isn't, a hose isn't going to get as hot on the outside diameter as you would with just a pure piece of tubing. So you're obviously going to get much better heat transfer if you can use a piece of tubing.
Oh, all right. Gotcha. Yeah. Thanks for your question there, Ray. But that is it. That's all the questions we got. Thank you all for your questions submitted here. Just a couple of things here that we'll wrap up on. So after the webinar, you should be receiving a follow-up email with some useful reference materials that'll help you prep for the winter here with your steam systems. And obviously, if you have any more questions or concerns, or you need some help, we always offer that you schedule a virtual meeting with our field engineering team, and that's at michigan.swagelok.com. And look forward to our next webinar, which will actually be in 2 months here. So we'll be covering tools, both online and physical tools here. And that one will be in October 21st, 2021, and we'll be at 10 a.m. again. And for any questions, concerns, or feedback for the webinar, you can always email us at solutions.michigan@swagelok.com. And I want to thank you all for joining us today. And be sure to visit our website, michigan.swagelok.com, for our past webinar series and future ones as well. But thank you all again, and have a great rest of your Thursdays.
Yeah, thanks, everybody.